Okay, so I have a fair bit to talk about and not as much time to do it, so I'm going to go through real quick. I'm going to talk a couple slides about INT, some risk reduction testing, some performance level testing, but we're going to start with a few of the old PR slides to show you some cool pictures and get a good positive feeling going. So if you have not seen it before, this is the CGI DM. The cutaway here and the two transparencies give you a good idea of just how complex this thing is. This is one of the more complex components that we've ever flown on anything. And the real picture there gives you a nice look at what it looks like with all of its thermal harnesses installed and the internal harness routed. Here they are on the bench. You've seen this before, but DM1 is in the back left corner, DM2 in the foreground there, all nice and shiny and gold for thermal regulation, totally. This is how it works. So the DMs are based on an electrorestricted material that when you apply voltage to it, it shrinks. So you embed platinum electrodes into the actuators, you cut them into a 48 by 48 grid, and then you bond a slab of fused silica on the top. And that slab of fused silica has been milled out to have individual posts that reach down to the actuators themselves so that every actuator has a nice independent control over a local part of the face sheet. These modules and other adaptive optics modules have been built by Zionetics for JPL and others for decades, going back to Hubble at least. What can you do with those actuators? Well, you can do a fair bit. So there is not much in this presentation that I get to claim unique credit for, except this slide. This is all. Is
that Frank Zappa on the lower left?
No, it's Lebowski. That's the dude. Yeah. These are the other people that get to claim credit for a whole lot more than that. So of course, I'm giving the presentation, but it took an army to produce the DMs, and I had to downsize the font to fit everyone on the screen, and I probably still forgot some people. So thank you to everyone who contributed. A couple notes before I go any further, just about data in this presentation. So the orientation of all data will be view of the upright DMs from the front. This might contradict some plots you've seen in papers or so forth. Sometimes that's for a good reason, being that they have flipped the DM orientation to be what it looks like on XCAM. Sometimes it is for a heretical placement of the origin, which, for example, John, Christ, and I continually argue over. But you can localize yourself. DM1's dead actuator should be in the bottom right, and the crosstalk region of DM2 should be in the bottom half, slightly larger on the left-hand side. Also be careful with units whenever you're looking at DM data. The two most common mistakes are surface figure error versus wavefront error. DM is book kept largely in surface. System level is book kept largely in wavefront. There's a factor of -2 between the two. And then there's also free stroke gain and free stroke ratio, which is very nuanced, and I'm not even going to bother trying, but catch me offline and I'll be happy to, or Brian Kern will be happy to explain the difference between all of those. So a couple slides on INT before we go into the test kit. This is the overall INT flow for the DMs. I'm putting this up only to demonstrate that there's three main levels of module maturity. The first is PMN module, where you have the actuators and the electrodes, but you don't have an optical surface yet. So the only information you can get is electrical. The second is the front end assembly, where it's bonded into the bezel and it's got the face sheet on. You can see through the face sheet and you can get optical performance data out of this. And then finally, there's the full assembly level with the coated face sheet, full rigid body mount. And that's where we get all of our for the record runs. Shout outs to two pieces of critical GSC that JPL had to build custom. One was this electrical gantry. Pour one out for the technicians who had to figure out how to make this work, measuring metallized pads, extremely sensitive, delicate nail pins after they were soldered to the backside, and tiny little pins inside of nano D connectors, because we did all three of those. This also had to be capable of measuring 10 to the 11 ohms of resistance accurately, which is far more difficult than you might think. Second critical piece of GSC is the vacuum surface gauge, or VSG. This is the second iteration of this. First has been run by John Trauger and company for decades. We built another one for CGI. This is a vacuum Twyman green interferometer that had to have TVAC capability so it could swing the DM's thermal environment throughout the entire range of its temperatures. We attempted to have tens of picometers of resolution here and wound up with about 100. And this was used as our venue for all of our optical performance testing for the DM. Okay, start with some risk reduction testing to call out the importance of doing these electrical tests at the very beginning. So there's 3 main electrical tests that we did going back as far as the first delineated actuator modules. Those are your capacitance measurement, that gives you an idea of what the stroke is going to be. There's the parallel resistance, that gives you an idea of what your leakage current is going to be. And then there's the series resistance or contact resistance, that tells you how good integrity you have in the signal chain of the DM actuators. We did these for 7 modules and then down selected to 2 based off of certain things like you can see in the capacitance and parallel resistance measurements for DM1 that it has its dead actuator. You can see if you read into the tea leaves a little bit, a pattern in the capacitance measurement for DM2 that wound up being in a crosstalk region. And believe it or not, we chose these 2 because they were the best. Okay, next thing we did as a risk reduction was at front end assembly level. We subsampled with a precision microscope all some pusher pads spread out across the grid. Then we analytically reconstructed what we thought the grid should be, overlaid it with a high-res photo of the pusher pads to make sure that our grid hadn't drifted or wasn't warped in any significant way. As part of this measurement too, we measured the face sheet thickness. This is very important for the DM because it determines your influence function. If you go too thin, you're going to see significant quilting print through from your actuator motion. If you go too thick, you're going to get a broad influence function because the face sheet is resisting the actuator motion. So you're trying to hit a nice sweet spot in the middle of those where you get a nice influence function and as little quilting as possible. This is really just an excuse, though, to show you this picture, which is one of my favorite of the DMs. This is a high-res photo looking down the gut of one of those glass posts, backlit, and it has this wonderful, weird alien texture that I love freaking people out with. So, okay, on to the actual for the run performance testing of the DMs. So first is look at the stroke of the 2 DMs. This is one picture of that. This is giving you an idea of sort of the 2D distribution of the strokes and how uniform they are across the surfaces. Note that DM2 here is crosstalk corrected. Hold on to that for a second. Talk about that. Here's the other portrayal of that, the typical S curves that you've probably seen when talking about DMs. Grayscale here is every individual actuator. Red curve is the average. So our average sat at max stroke in the mid 400s or so, and we had a distribution mainly between like the upper 300s to the lower 500s, which is actually a little bit less than what we would have liked, but it wound up being perfectly fine for TTR5, and we expect much better than that on orbit. Like I said, crosstalk. So DM1 didn't crosstalk at all, and DM2 definitely did. So what you're looking at here is if you apply voltage to electrical pad IJ, actuator IJ motion is the center plot. That's the intended actuator for the voltage that you applied. All of the other plots are how much the neighboring actuators moved. And as you can see, DM1 crosstalks upward significantly. For a certain region, poke one actuator, the actuator above it moves. So this was inconvenient, but the HOFIS team responded very well. This is included in the model, and it complicates the mathematics, but it doesn't ruin the operation of the instrument. Next up is thermal dependence. So you heard from, I think, Ilya, who pointed out the thermal control and how well the thermal control group did for CGI, particularly the DMs, which reached down to like sub-millikelvin stability. This is the other part of that story, which is this is the sensitivity to thermal disturbance of the DMs. We expected about 1 nanometer RMS surface difference per degree Kelvin. That's about what we got. And it's a good thing that the control does significantly better than its requirement because it performed to its requirement and this performed its requirement. This would be, according to the FRN budget, about a 7 to the minus 9 effect. And most significant here is that you can see the nominal HLC control pattern in the thermal data. It's not just a piston term. Also, you've probably heard, and definitely you've heard if you've been following the DM saga, that both DMs suffer a significant cylinder term on their surfaces when they are fully desiccated under vacuum. There's DM1s, there's DM2s. So the static portion of this was ameliorated a lot by the heroic efforts of the optical alignment team at system level to correct this with static optic alignment. But I would like to point out that the time scale was still a little painful, because you can see, well, maybe you can't on the bottom because the font's really small, but out here is 600 hours on the right side of the plot. So on orbit, when we've got multiple weeks between launch and commissioning, not a huge deal. In TVAC, when you're paying God knows how much money to run a vacuum chamber for multiple weeks, much bigger deal. And also when you're at home during COVID, taking this data, it's a much bigger deal. The root cause of this, we could spend a lot of time talking about, but in brief, we have these 2x50 header bars on the back, providing the electrical signals. Those shrink as they lose moisture, and as they shrink, they pinch the nail pins, and as they pinch, they bow out the front side of the surface. There you get your cylinder. That also explains, by the way, why this is Z4 and Z6, because those are the two constituent Zernikeys of a cylinder. Last notable significant thing about the optical performance of the DMs is the drift that we noticed. So what we did for this data, and we'll show a little bit more on the next slide, is we set a mean 40 volts to the DM surface. We referenced relative to an unactuated portion of the surface, and we just watched the piston of the surface evolve. And this is the plot that, if you've read John Christ's Jadis paper, you have seen. There is a long-standing, understood logarithmic behavior called creep drift, and what we saw was not logarithmic and much longer, which, if it were piston, would not be a huge deal. But if you apply the HLC control map, again, you see in much longer drift characteristic that the HLC control map shows up in the measured drift data. And indeed, if you go in and you interrogate the behavior of each of these individual actuators, you will also see that same non-logarithmic behavior, about proportional to the voltage that it saw when it jumped into the HLC control map. So this did have significant impact for ConOps. This is why we now apply our control maps immediately following a CGI observation, so that they can sit there for the entire time that Wide Field is doing operations, so that they're ready to go and have hopefully exhausted their drift when we get to the CGI operations the next time around. It's also why the fault protection people were extraordinarily frustrated by me as we declared that you should never turn the DMs off under any circumstances.
Been there.
Yeah. Okay, so just real quick through a couple lessons learned. I have split these into two groups because I thought I might have two groups of people here. One group planning for habitable worlds and one group being the consumers or users of CGI. So for those of you planning for habitable worlds, I thought the most important thing to impress would be to build early so that you have time to cherry pick your modules. And as you're doing that, do trust the electrical test data that you get. So motivation for the first bullet point. These are lovely plots from John's paper, which I really love. The one on the left sort of shows you how important each actuator is to the different choreography modes. Red, very important. Green, blue, not as important. Dead actuator on DM1, we got really lucky because it's in the yellowish zone. So it hurts us a little bit, but doesn't destroy us. For Hab Worlds, if we had a dead actuator in the red zone, which will hopefully be larger as it will be hopefully an off-axis, a dead actuator is a no-go. And second, just to sort of reinforce, you can trust the electrical data a fair amount, which means you can build modules and test it, build it, test it, build it, test it, and pick the best. So this is showing the loose correlation between capacitance and ultimately measured gains for the record. One nice loose correlation between the two. And here is DM2 again, where if you read into the tea leaves, you can sort of see the fact that you could predict, or a significantly experienced SME could predict that you're going to see crosstalk on this DM. The last 3 points for habitable worlds are kind of obvious, if you will, but I'd be derelict of duty if I did not mention them. Decouple your interconnect mechanically from the optical surface as much as you can. Pay attention to your thermal environment and get a better test bit than we had, or give us a little bit more time to develop it, because 100 picometers held us back a little bit on testing the deals. For consumers or users of CGI, I'm happy to say that most of these things are things that you should just be aware of, because the ops team and the modeling team have already done a great job of accounting for most of it. So be aware of that crosstalk region. It complicates the math of solving the DMs a bit. Be aware of the dead actuators and the fact that those impose significant behavior around the neighbor rule in particular. For those Z4 and Z6 terms, this bad cylinder, note that the static optic compensation wasn't perfect. So there's still a lingering, fairly large term there, which means if you come up with a choreography mode that just starts railing actuators, be sure to check the modeling team before you plan to use it. And then be aware of your timescales. Don't plan ops that expect to work on the order of hours, because you are actually going to be waiting 5 to 15 days before that settles down. And again, these are all already included in the model, already included in the tools, but be aware of them as you're using CGI. So that is it for me. Hope I gave us a little bit of time back.
Questions for? Yeah.
Yes.
If you made the DMs again, you'd make them curved at room moisture so that when they dried out, they're flat. How would you deal with that?
I would use different interconnect design.
Different
That was picked because it was fairly mature when we were doing the TRL6 down select, but I think we have better ideas that hadn't reached that level of maturity. I think going into Hab Worlds, we definitely have ideas that we can mature to fight. Yeah.
The question, the crosstalk, do you think it was electrical or?
It is electrical. So what happens is, if you want to go really deep, when they construct the PMN with a binding agent so that it holds together. And then when they bake out the binding agent, the entire module shrinks by about 20%. And when that happens, the middle layers can sag, so it won't shrink uniformly. And then when you do that, the electrode pattern on the back will sag. And then when you slap a uniform metallization grid onto the back of it, the pads start to either miss or actually overlap with the electrodes from the actuator one higher. And then
So some you get lucky and some you don't.
Yeah.
The yield.
Yeah. And it's also a module size thing. So for example, if you did 24 by 24 or 36 by 36, you'd probably see this less effects.